Alright everybody, welcome to part 2 of this video. In this video, we're going to find the drift component of JWT, which we're calling mu of J. We're doing that because it's what our optimization asks for. And we're going to use that, plug it back into the optimization, and find the optimum portfolio pi star. So to do that, we're going to have to use Ito's lemma, because remember that mu J we defined as the drift component of dj, component of dj. So we need to know what is dj. So let's do Ito's lemma. That should be second nature by now. dw, so first derivatives plus the second order derivatives, mu squared j. Let's do the sames first. Squared j. And obviously, you know, if you know some of these are going to be, like dt squared is always 0, so you could just skip that on a test. dw dt, and remember for this cross term there's two ways to make it: w first, then t, t first, then w, so we need a 2 here. Very good. Let's look for our zeros. We know that dt obviously is 0, we talked about that. dw dt, is this 0? I think yes. So dt dt, that's 0, dt dz, that's 0, so this is just 0. So we only have 3 terms to deal with, and we've written them down nicely already. So just fill it in. This is going to be JW and then DW. Now I'm going to skip, I'm going to cut one little corner here, and that is that recall that we only care about this drift term, number 1. So we don't need DZ. We can just throw it away. So I'm just not even going to write it. dj dt, and then 1/2 are jww and then dw squared, which is wt squared pi t squared sigma squared dt. The other thing, remember, is that we're actually looking for 1 over dt of the drift term, or that the drift term is defined as 1 over dt, the limit, you know, and then minus that subtraction part to get rid of the dz. So these dt's will go away. So our answer for mu of j is just going to be equal to exactly what we have here with no dt term, minus r, plus jt plus 1/2 jww wt squared pi t squared sigma squared dt. Whoops, no dt, no dt. Bad Jesse. Bad Jesse. Great. So we're going to use this, remember, to get our first order condition, because we know that we want to maximize this mu t, or this mu j, with respect to pi. So our first order condition will just be d mu j over d pi t equals 0. And that will be equal to 0 equals, now in here we'll get mu here, or we have a pi here, so that stays. We'll get jw wt mu minus r. This jt goes away, and then over here this 2 comes down and gets rid of our 1/2. So we'll have jww wt squared pi sigma squared, and that equals 0. So let's rearrange to solve for pi. jww wt squared sigma squared pi is equal to minus jw wt mu minus r. So that pi is equal to, drumroll please, jw over w jww mu minus r over sigma squared. And that is our answer. We're going to do one little thing to clean it up. We can do two little things to clean it up. The first is that we're going to define this term gamma just as before, and we're going to define it as the inverse of what we have over here, the inverse of it. So j w w w over jw, so that our pi star will become 1 over gamma times mu minus r over sigma squared. The other thing we can do is to recognize that this mu minus r, this is the risk, this is the price of risk, the risk premium, and we could call that lambda. We could say lambda equals mu minus r. So that at the very, very end, mu star is equal to 1 over gamma. We'll give it a j subscript because it does depend on the function j, times lambda over sigma squared. And that is the optimum portfolio. So we see again that preferences don't enter. And also we're kind of confident because let's compare this with our result from the Merton framework, which, and I'm doing this from memory, so I apologize if it's not perfectly correct, was 1 over gamma matrix sigma inverse mu minus r1. So what we have here, there's only one asset now, of course, but we have the rate of return on the risky asset, the deterministic part, minus the rate of return on the risk-free asset, divided by the variance or the volatility of the market. And well, here's exactly what we have. We have exactly the same term on top and exactly the same term on bottom, just that now the market is composed of one good. So it's not a matrix anymore, we just divide. So that's nice, we got the right answer. So we're actually going to keep working with this. We'll take this pi star now, and we're going to use that in a utility function to actually compute the terminal utility of this investor. Because remember, our actual question was, what is this U bar of W big T? So we can use this optimum portfolio to compute the optimum path of wealth accumulation, and then we can find out what is this utility. But we'll have to make an assumption about the utility function in order to do that. So I will see you in the next video.